Okay, so let's give it another shot, right? So we were talking about line wedge formula, okay? When you have this black wedge, it means, yes, that the bond is directed towards you from the screen into your direction. When you have a dashed bond, it is directed behind the screen in the back under the page, call it whatever, okay? So this way we can represent the three-dimensional structure of methane in a two-dimensional picture. To be fair, just like it is very important when you talk about the mechanisms, but when we talk about structure, we would use expanded or condensed structural formula for the most part. So when we add another carbon, look at this. 2 carbon atoms, each of them forms 4 bonds. 1 bond is formed between themselves, and 3 others formed with hydrogen ions.
Is that the representation of like a saturated?
It is another, yes, exactly. It's a saturated hydrocarbon. There are no double bonds. It's a fairly simple structure, okay? And again, this is dash wedged formula, dashes, wedges. Wedges stick out, dashes kind of go back behind the screen. Expanded structural formula makes sense only if you really focused on hydrogens. In other case, condensed structural formula is more than enough. Okay? So, now, remember the shape at each shape of each carbon? It's tetrahedral, right? Okay, so here's the thing. If we will try to do this wedge dash formula, then this carbon, bless you, for instance, since all these bonds are in the plane, okay, of the screen, right? So we can have 1 hydrogen here, hydrogen behind, and hydrogen in front, okay? At this carbon, we already have 2 bonds that are in the same plane, so 1 hydrogen has to stick towards you and another be behind the screen. Same is true for the 3rd carbon, so here's our wedge, here's our dash, okay? And finally for this one, we can put a hydrogen in the plane, and another here, and another here. My goal in representing this is to show you that when we look at the structural formula, expanded structural formula, it feels like the molecule is two-dimensional. You see what I'm trying to say here? So it's the entire molecule is in one plane, which is not true. Because when you start looking at the wedge dash formula that I have at the bottom, these hydrogens are sticking out all the time. Okay?
So those dashed triangles.
This one?
Yeah.
Uh-huh.
So that indicates that the hydrogen atom is like
behind the screen, yes. Or page, in this case, screen, yes. And the wedge indicates that the hydrogen is in front of the screen. Okay? So you see, this answer, in my opinion, is kind of boring. We said it in a very beginning, but we also demonstrated that a molecule of a hydrocarbon such as butane is going to have not just a plain, like it's not, it doesn't, all atoms do not lie in one plane. The architecture is actually quite complex. Okay. First category of hydrocarbons, actually we were talking only about them so far, are alkanes. Okay? So in alkanes, all bonds between carbons are single. Well, bonds between carbons and hydrogens are always single because hydrogen cannot make more than one bond, right? All good? Understood? So no double bonds. These covalent bonds between two carbons or carbon and hydrogen are very strong. So there are not a lot of reactions that you can do with them. Okay? So they are chain-like. They can be straight chain, well, chain like this. They can be branched. Okay? But nevertheless, all bonds are single. All their names end with A and E. And there are prefixes to indicate how many carbon atoms are found in each molecule. So, before we get there, I want to talk about line angle formula. So imagine I'm going to write a collapsed structural formula that we have a molecule of butane. Okay? This representation, I hope, makes sense for everybody. When we draw a line angle formula, we imply that at the end of a line or at an angle, there's a carbon. Carbon, 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 carbon. I'm putting the dots not because they are required, but to, emphasize the importance of it. Good? We do not put any information about hydrogens in that formula. You may ask, wait, why? How many bonds can a carbon atom form in one organic compound? 4. So this carbon forms right now how many bonds? 1, right? Just 1 to another carbon. So it has 3 extra bonds to form with hydrogens, right? So 3 hydrogens right here. This carbon forms 2 bonds, okay, with 2 adjacent carbons. Am I making sense? So it can form bonds only with 2 hydrogens. Okay, now I'm going to give you a mental exercise. This is an actual line angle formula of a compound. How many carbons does this compound have? 5. Each end is a carbon, right?
Like the carbon in the center, and then each of those 4 would be the hydrogens.
No, because it is a line angle formula. Huh? I'm going to finish, then you ask, okay? It is a line angle formula. At the end of a line, it's a condition. It's a carbon. This is the end of a line. This is the carbon. This is the end of the line. This is the carbon. Here and here. And an angle or a crossing is also a carbon, so that makes it 5. Alicia, question? Okay. Then we have another question for you. Each of these carbons at the ends of the line, how many hydrogens do they form bonds with? 3. Yeah. Each of these terminal carbons, has 3 extra bonds for hydrogens. How many hydrogens does the central carbon binds to? 0, yeah. It's just bound to 4 other carbons. Okay? Does that make sense? Yes? Okay. Let's move on. Okay. I'm going to make it larger. So these are prefixes that you need to know. Meth 1, eth 2, prop 3, bute 4. These make absolutely no sense. So this is memorization. Next ones, especially if you encounter other medical, physical concepts, pent, 5, pentatonic, hex, 6, hept, 7, oct, like octave, 8, non, 9, dec, like decimal, 10. Questions about the naming? Only up to 10, that's it. Now, can you please help me find a mistake in this table? To be exact, 10 mistakes. Or 1, yes.
In the number of carbon atoms, the line angle formula, would that be 2 carbons?
Exactly. Line angle formulas, look at this. Line angle formulas are shifted 1 step up. There is no line angle formula for methane. It would be a dot. So this should go here, propane, butane, and so on. Okay? Making sense, everybody?
But are those actual mistakes, or is that actually how it is?
Somebody fucked up the table during the publishing. Yeah, that what happened. It's a human mistake. It is a human mistake. Somebody just screwed it up. Okay? So, for the most part, we will be using condensed structural formula. So, for instance, this shows you that this carbon is connected to 2 adjacent carbons and also 2 hydrogens, but we don't expand them because they usually don't play a terrible amount of roles in chemical reactions. Okay? Now, in some cases, you need an expanded structural formula because you want to show how bonds are changing. Okay? But this is essentially, here, is a relationship between the expanded and the condensed structural formulas. So, I'm going to give an illustration. So, alkane can be represented in several ways. It is true. Let's try to represent it. We're going to try to represent molecules of propane. Okay? So, how would you represent a molecular formula? Propane, 3 carbons, 8 hydrogens. Okay? Ball and stick, folks. I'm not the greatest artist, so if you don't mind, what I'm going to do, I'm going to use instead wedge dash. It's just easier for me to draw. So we have 3 carbons. Okay, this one, those hydrogens are in the same. Okay, like this, like this. Like this. I would be good at drawing balls and sticks, so pretty much the same idea, right? Now, what about expanded structural formula? So we have 3 carbons aligned, middle one is connected to 2 hydrogens, and terminal are connected to 3 hydrogens each. Condensed structural formula. Instead of the first one, we would do CH3, second one CH2, and the third one CH3 again. And line angle, remember, a carbon is at the end, a carbon is at the angle crossing. So that's it. Okay? All good? Right. So, something that's important to understand. All these formulas that you see are equally valid. The only reason why you would change the representation, if there is a reaction that you want to show where, like the actual interaction takes place or something like that, you would use different condensed structural formulas. Other than that, there's no difference between them. Okay? Now, as a matter of fact, before we move on to cycloalkanes, I want to chat about the universal formula for alkanes. I'm going to give you a mental exercise. I want you to find a pattern. I'm going to write down the formulas for alkanes, consecutively increasing the number of carbons. Check this out. Try to find sort of a pattern, a relationship between the number of carbons and the number of hydrogens. Go on. Say again? I keep... What would be the formula if we have n carbons? N carbons.
So carbons go up by 1 and the hydrogens go up by 2.
Well, how would you build it from, like... Say again? Say again? Say it again.
I would say it would be 2 plus 2 times the coefficient of C.
Usually it's written the other way around, but you're absolutely correct. H to n plus 2. Yes. All alkanes, all of them, follow that formula. No exceptions. Because it is defined number of bonds. Right? Okay? Now, cycloalkanes. So basically, you can think of it this way. These carbons each form bonds with 3 hydrogens. Now, if you look at this, if each of these carbons give up 1 hydrogen, so giving up total of 2, hear me out. if this carbon and this carbon give up one hydrogen, they have an opportunity to form a bond between themselves. So you need to give up two hydrogens from an alkane like this, to form a cycloalkane. What are going to be coefficient? What is the subscript at hydrogen? Well, it's N. I don't know what N is. What if N is 24? Exactly. That's it. This is cycloalkane. Okay? So I don't know much about cyclobutane or cyclopentane. I can tell you that cyclohexane is a very popular solvent in organic chemistry, and I can tell you something else. This molecule is fairly unstable. There's a lot of tension, like literally tension in the bonds. So it makes it easily very, very flammable. Interestingly, for some time, cyclopropane was used as a general anesthesia gas. And it worked perfectly well. It was absolutely neutral. It would evacuate itself out of the lungs. Like, it was easy to administer. The main problem was it was so flammable that there were accidents. Now, in many alkane molecules, hydrogens can be replaced with different substituents. It can be other so-called alkyl groups. It can be halogens. It can be functional groups, so on and so forth. Okay? So, the concept of substituents here gives us the opportunity to talk about the concept of isomers. Okay? And we're going to right now focus on structural isomers. This is a formula of a molecule of butane. Now, if you rearrange the atoms here, rearrange the bonds, this is also a molecule of butane. It's going to have a slightly different name, but it still has 4 carbons, and if you count, 10 hydrogens. These 2 molecules are isomers. Okay? So, what we're going to try to do, we're going to draw 3 isomers, the molecule of pentane with 5 carbons. I'm going to do collapsed structural formula first. Go on. Tell me what I need to do. We need to draw a structural isomer. Isomer in which you have same number of carbons, same number of hydrogens, same number of bonds, but atoms and bonds are rearranged. Any suggestions? What to do with that molecule? How can we shift a carbon? Go on, just tell me. You don't have to raise your hand.
So like the second or third, you can just get rid of it, squish it together so there's just 4 in a line, and then you can branch it out from there.
All right. So this is what you're suggesting. Correct me if I'm wrong. Right?
And you can put another one on the second one, and that could be the third.
Okay, so you want to put, hold on,
So yeah, that's
this one Move, okay.
And then you could have another one by moving the CH3 to the second area.
Like here?
Yeah.
Okay, let's do it. Let's take a look. Let's take a look.
Your face makes me nervous.
You shouldn't be nervous. Is there a difference between
Oh, no, there's not.
A and B? There's no difference. They effectively mirror images of each other. Does that make sense? So no, there's no difference. So this is not an isomer. How do I do one? There's one more. Start the same way you did before. You shortened the main chain, right?
Could you do like a 3 in a row? And then
Okay, let's do 3 in a row. Not two, hold on. I don't want to reveal it. So I have 3 in a row. What should I do?
like a 2 chain from the middle one. Yeah.
Okay? That's an isomer. 12 hydrogens, 5 carbons. Okay?
So it's just an isomer is just like a different way of rearranging.
Atoms. Yes. There are some conditions. Why? So A and B, they're not isomers. Why? Because they are mirror images of each other. Does that make sense?
Yeah.
Yeah. So we don't consider them. Those are the same molecules. Okay. Let me know if I need to stay on this. Since the exam is multiple choice, you won't have to draw anything, but you will have to recognize isomers. What is the isomer here or whatever. Okay, so yes, that's going to happen. Substituents. So first type of substituents is alkyl groups. I'm going to give you some examples. If you don't remember, just tell me right away, don't remember. What is the name for this molecule with 1 carbon? Methane. So the alkyl group out of it is going to be methyl. Ethane. So you lower it by 1 hydrogen and stick out the bond ethyl, right? So basically you change A and E to YL. Sounds good? Okay. Halogen substituents. This is your 17th group. Fluorine, chlorine, bromine, iodine. So fluoro, so basically, fluorine, fluoro. INE into O. Okay? Make sense? The naming part? Okay. I want to know. So, these are common names because there's an IUPAC name and then there's a common name. Now, what we're going to try to do is to name this compound. So, how do you approach that? You need to identify the substituents. Are hydrogens substituents? They're not. So we have a substituent here and the substituent here. Okay? So the name of the bottom one, this one, methyl. The name of this, chloro. Now, first of all, how many carbons do we have in that molecule that are lined up? 5. The name for an alkane, pentane. For some reason my brain switches me to Russian alphabet. Pentane. Okay? Now the question is, how are we going to number? Why can't we do 3-methyl-4-chloro? Why can't we do 4-chloro-3-methyl? Can we? It's folks, there is no chemical sense. Like it's not a law. It's what a bunch of nerds agreed on. When you select the numbering, the sum of all numbers should be minimal. You were right. It is 2 and 3. Okay, does that make sense? So 2-chloro, 3-methylpentane, right? Good. Why can't I call it? Why we don't call it, and we don't, 3-methyl, 2-chloropentane? The sum will be the same. Substituents go in alphabetical order. Again, this is just an agreement. This is why I'm telling you, when I was studying this in college, hated it. Absolutely. Nomenclature, those are the most boring people that exist on this earth. Okay? Good? Now, when you make cycloalkanes, kind of same story, but here's my question. Why there are no numbers in that name? Ethyl cyclohexane. Yes, because all carbons are equivalent. What if I'd modify that molecule and put chlorine atom here? 2? 3. Yes. So now you need to assign numbers. And in order for these numbers to be minimal, it's 1 and 3, right? Because the alternative would be 1 and 5. Depending on how you count. Does that make sense? Huh? Okay. Do you need a number to signify where methyl is? Imagine that this molecule rotates around this point and the carbons are switching places. You can see that the ethyl substituent, it can be on any carbon, right? So it doesn't matter. So carbons are equivalent. Agreed? Okay. Now I'm adding second substituent. Now, in terms of their position, carbons are not the same, so we can give them numbers. Where should we start numbering? We should start numbering at either, it doesn't matter, seriously, we'll get back to this, chlorine or methyl. Let's say we start at methyl. How should we number? Clockwise or counterclockwise? If we do clockwise, chlorine is number 3. If we do counterclockwise, 2, 3, 4, it is number 5. 1 and 3 give us better number solution. Now we need to figure out which one should we actually start with. Ethyl starts with E. Chlorine starts with C. C is ahead, so it's going to be 1 chloro, 3 ethyl, cyclohexane. Do you feel my hate towards nomenclature? Yes. Now, obviously, half jokingly, because without nomenclature, we wouldn't be able to communicate without drawing formulas. But now, when you look at the entire name, you actually start from the end. You start with a heptane. You draw a chain, and then you start adding substituents. When you drew a chain, 1 can be anywhere. Can be on the left, can be on the right. I usually put it on the left, but it is fairly arbitrary. Okay? So, condensed structural formula for this compound. Butane, how many carbons? 4. Okay? Now, let's number from the left, shall we? So the first carbon is on the left. The substituent is chlorine. Okay? Then on the third one, we have bromine. Okay? So far, so good? So we got this. Now we need to place all the hydrogens. The first carbon, how many bonds does it already form? 2. So it has 2 bonds for hydrogens. Same story is with the carbon number 2. Carbon number 3, how many bonds does it have left for hydrogen? Just 1. And this one has all 3. Okay?
Could you go, not on the slide, but the previous one where it says draw the structure for 1,4, 1,2 dimethyl?
Absolutely. We can do that.
You draw that.
Sure, yeah. Well, not me, all of us together. How many carbons should I put in a line? Heptane. 7. Shit, I keep forgetting to which side I need to. Forward, okay. 5, 6, 7. Okay. Now 1, 2 on the left. Sounds good. 1, 2 dimethyl. Agreed? Sorry, no, my bad. 1, 2 dimethyl. 1, 2. Okay, we got this. 1 chloro. Good?
I just had a question.
Mm-hmm.
So it's a 7-chain line with the carbons, but why would you not include that methyl group on the end that's connected to the chlorine?
Say again?
Couldn't you also rewrite it as an 8-strand?
Uh-huh.
2 chloro?
Very keen eye. When I looked at it, yeah.
That's why I was confused. I was
So, okay. Let me explain the conversation. When you name a compound, you always select the line of carbons that is the largest. Check this. This line, how many carbons does it have? 7. But it's not the longest, because this line would be the longest. Because I needed to draw it down. Now, If it's 8 carbons, let's write a proper name. If it's 8 carbons, what's the name? Octane. And now we should number from the left to have the smallest number. 1, 2, 3. So what would be the name? Yes. 2-chloro, 3-methyl octane. 2-chloro, 3-methyl. Does that make sense? Yeah, fun with nomenclature.
So I have a question.
Go on.
Learning check 3.
We're getting there.
3. So if it's 3 bromo, why is it just 1 bromine like above the? You see what I'm saying?
Yes. This number does not show you how many atoms. It shows you where it is.
Oh.
Let me illustrate. So first of all, let's get rid of this, like do this stupid angle formula and just reposition this. Okay? Now, what I'm going to do, I'm going to replace this chlorine for Zach's question with a bromine. Okay? Opposition's the same. 1 and 3. Yes. Nothing changed. But both substituents are the same. So 1, 3, dibromo, butane.
That makes a lot more sense.
Excellent.
Are we adding the same prefixes then
To the number. Okay, I'm going to ask you a very, it's absolutely not a tricky question. And it's a fairly easy question, but it may be a little bit out of the box question. So we have dibromo. Can we have tribromo? Can we have tetrabromo? In some cases, can we have pentabromo?
Not there.
Why?
There's only 4.
Excellent. Yes. So here's the deal. If you have this carbon in this molecule, how many, let's say, bromo substituents can you add to it? 3. That's it, right? Like, you can have tribromo at the end of a chain. Which organic molecule can have tetrabromo? There's only one. And it would be a proper name. You don't need anything. You don't need any numbers. No, tetrabromo. No.
Well, I'm just thinking of 3.
No. The only one properly named will be this. And that would be tetrabromomethane. Okay? Where you replace all 4 hydrogens with 4 bromines or chlorines or fluorines, whatever. Okay? Does that make sense? You don't need any numbers. I know, I understand what you asked. Yes, we can have in this molecule, the one that we have here, I can put bromines here all I want. Totally. Yes, I can do that. And that would be tetrabromobutane. But we will need numbers. So it would be 1, 2, 3, 4. Tetrabromobutane. but only with numbers. Without a number, it only can be tetrachloromethane. Okay? So, properties. We're going to talk about properties, finish alkanes, and take a small break. Properties. Flammable. These four are burned as gas. In practice, propane is the main component of natural gas. We also isolate butane for high energy camping stoves. These are liquids. You see, they for some reason copied the same statement. So pentane, hexane, heptane, octane, and above that, they have they liquids. These are liquids with higher boiling points, and paraffins are alkanes with a lot of carbons. Okay? Trying to think of a good example. Yes, I do have actually a good example. When you fuel your car, there's a number. Like there are 3 numbers usually, right? At the station. What do they mean? Like what does that mean? 87 or 92 or whatever, 95, 93, I don't remember. 91. It's an octane number. So here's what octane number, the idea is. When you burn fuel in the engine, it has to burn very fast, but without actual explosion, without a detonation. If you've ever heard muscle cars with this sometimes exploding sounds coming out from under the hood, that's the detonation in the engine. Okay? Now, the octane was selected as a standard for the quote-unquote capacity to detonate in the engine. And all fuels that we use in the cars are ranked by comparing their capacity to cause those detonations to octane. Making sense? Octane, if octane is 100, anything lower, the lower the octane number is, the more chances there that the fuel will actually explode in the engine. Do you understand what I'm saying? So, if you put, like, I drive an old minivan with old engine and compression is really low, I can put 87. If I would drive Ferrari with a greater compression, the propensity of the engine to detonate at this low number would be greater, so I need to put like 91 or 93 or whatever numbers are there. Does that make sense? So it actually, like you, in the modern engines, you probably won't be able to put anything with an octane number like 80. Your engine would wear out very quickly. Okay?
What does that have to do with like, 'cause it's like, it seems like the lower the octane number would be like unleaded than leaded.
They're all unleaded. Now so what you're referring to is leaded versus unleaded fuel. Lead, I think it's ethyl lead, trimethyl lead, was added to reduce the detonation properties, which contaminated the environment, blah, blah, blah. Okay, let's skip it. Now, all fuels are unleaded, but the ones with higher octane number are more expensive because they require some extra steps in terms of treatment and rectification and purification. This is why they're more expensive. And because people with Ferraris can pay more. Okay. 1 to 4 carbons, heating fuels. Okay. 5-8, gasoline. 9-17. Look how more and more dense these substances become. So gas is really like light and can float on the surface of the water. Motor oils, kerosene, diesel, kerosene and jet fuel is the same thing pretty much. They are denser. Okay, this. Waxy solids at room temperature, paraffin, various coatings. Vaseline, really long chain carbohydrates. Hydrocarbons, I'm sorry. Okay, but, so yeah, petroleum jelly comes from petroleum, yes. But I'm going to tell you something else. The main component of asphalt, bitumen, it consists of hydrocarbons with a number of carbons like in hundreds. When oil is being rectified, it is separated into these guys, and it's like lower and lower. And at the bottom of the rectification column, you're going to find asphalt. Okay? Let's take a break.